Everyone, and welcome to this new lecture of Advanced Geodynamics, Theory and Modeling. In the previous week, we've discussed about entropy production, total energy balance, elasticity, and viscosity. So remember this nice example from the Europa Park roller coaster and the initiation of subduction. So we basically discussed effects of heat transfer and how entropy is being produced. Remember this equation, the S dt, where S is the entropy and T is time. Q dot is the rate of heat transfer, T is the temperature, and this is the net entropy production. So in the case of heat exchange between a hot rock and a cold rock, we had the entropy production, which was calculated. Remember, the universe entropy, the SDT universe, is the sum of the entropy production in both of the rocks here, and it's only positive if the hot temperature is indeed larger than the cold temperature. So heat flows only from the hot to the cold. That's the only way to have positive entropy production. That was the realistic scenario. Coming to mechanical systems, we've introduced the notion of total energy. So we have the total energy E, which is the sum of internal energy plus kinetic energy and potential energy. We've introduced different types of potential energy, being gravitational potential energy or elastic, strain energy, and the kinetic energy defined here. In the case of a spring, we've derived the work coming from the force which is applied on the spring, and we discussed that this type of deformation is reversible and does not result in the production of energy. The mechanical energy is stored temporarily as a potential energy, while in the case of viscous deformation, we had permanent deformation, non-recoverable. This means that the mechanical work is being dissipated and there is a feedback. So the temperature can be produced by viscous dissipation due to the deformation, and we even discussed the possibility of this influence on the generation of subduction zones on the Earth. Now the topic of today is slightly different. We are going to talk about melting and crystallization, yet it will be very related because we're going to discuss about the entropy production too. So melting and crystallization, of course, are key processes in geodynamics, and they can occur in any type of plate boundaries, so from the divergent context to the convergent context. And they also can be affecting the interior of plates, so in the intraplate setting, so if you have a hot spot, or even in the location of petty spots, you can have the transfer of melt that was generated at the base of the lithosphere. Of course, this all has important consequences for the surface of the Earth, because magmatism has a surface expression which is volcanism, and so you can have the generation of huge volcano, and that's, you see, this is the Mount Semeru in Indonesia. This would be the Cleveland volcano seen from above, so that's a fantastic NASA picture from this volcano located in the Aleutian range. So different types of tectonic context also means different types of melting. As you may know, to melt, for example, mantle rocks, you need to cross the solidus. This can be done by decompression melting in the mid-ocean ridge. This can be caused by heating, so if you're just heating up in a thickened crust sediments, they will start melting. Or flux melting is when you're basically fluxing or changing the composition of the mantle by adding water, which then lowers the solidus temperature and then induces melting. So let's go back to the different to the energy definition. this is the internal energy. That's a slide from our first lecture. Remember, the internal energy is the energy which is due to the microscopic motion and the particle interaction. So, in fact, it includes the kinetic energy of molecules and the potential energy of the molecular interaction. So think about at a very tiny scale, you would have intramolecular forces and chemical bonds. This is potential energy. It would take a lot of force to actually break these bonds. And you have also agitation, so vibration of the crystalline structure, for example. This is kinetic energy. So this internal energy, it can be formulated as an extensive variable. It is a state function, and it can be formulated in a specific way. For example, if you make it intensive by expressing it per unit mass. We can do it per unit volume or per mole. That would be the intensive expression of this. Now, since we are discussing melting and crystallization, we're going to talk about reactions. We need to introduce enthalpy. So enthalpy is, in fact, the internal energy plus mechanical work under the form of pressure times volume. So that's the pressure volume work. The pressure volume work here, this mechanical work, is the energy which is linked to expansion against an external pressure. So we form a new function, H equals U plus PV here. This variation of enthalpy, they are caused by variation of internal energy or variations of pressure and volume. So if you want to change this thing, we need to vary these components here. The enthalpy is a state function that incorporates the effect of expansion work. So it incorporates this term, and it is used a lot for dealing with transformations of materials such as melting or solidification. It can be also used to model phase transitions. The rate of enthalpy can be expressed by taking the time derivative of H. So remember, H was defined as U plus PV, so we take the time derivative of U and we take the time derivative of PV. So we have to use the product rule here. dH dt is du dt plus V dP dt plus P dV dt. This is how to formulate the rate of enthalpy. The rate of internal energy was defined as du dt is equal Q dot minus W dot. Remember, the heating rate and the work rate. Now we can express the work rate, for example, as P dV dt here. And if we substitute du dt into the expression of the H dt, so we're going to put it right there, we end up with this expression. dH dt is Q dot minus P dV dt plus V dP dt plus P dV dt. Of course, these two terms here cancel out, and we end up with the expression of the enthalpy rate, dH dt, is Q dot plus V dP dt. Okay, why are we doing all of this? Just to come up to this expression, actually, how to change the enthalpy. We change the enthalpy by having a heat input rate and the term V dP dt. This is the general case. Often the constant pressure case is considered, and in the case the pressure is constant, of course, dP dt becomes 0, and the rate of enthalpy will become simply Q dot. Here I add the label P. Q dot P will mean this is the heat added at constant pressure. So at a constant pressure, the heat added equals to the change of enthalpy. So for a lot of processes are acting at constant pressure, and then the enthalpy just reduces to this. One important point is how to relate enthalpy and temperature. In the previous lectures, we've been working with internal energy, and we were defining internal energy as rho C times T. But I've never said any detail about this C. So the C which is here is CV. CV is for constant volume in a way. So it's the derivative of the internal energy with regard to temperature at a constant volume. If one works with enthalpy, then one defines the enthalpy as rho Cp T. In that case, Cp is the derivative of enthalpy with regard to temperature at constant pressure. So Cv and Cp are different. So they come enthalpy and internal energy, they are different state functions. So Cv and Cp have different values. And typically Cp is larger than Cv because the enthalpy incorporates the effect of P dV dt. So let's go to the case of melting of a pure substance. So let's imagine a block of ice here. We have hot surroundings on each side. So heat is going to be transferred to the ice. So the temperature in the ice should rise. Now we have a diagram that shows T versus H here. H being the enthalpy, we increase the enthalpy, and linearly we increase the temperature, and the coefficient will be Cp. But at some point we hit the melting point, so we reach the temperature for the fusion of ice into water. What will happen here? Not much. The temperature has to remain buffered because we need to heat the material to overcome the latent heat of melting. So temperature will remain constant until the delta H, or the latent heat here, is overcome. Once enough heat has been supplied to reach full transformation of ice to water, sensible heating can take over again. So we make the distinction here between sensible heating, which happens without when the material is not going into a transformation, and the latent heat, which is the latent heat of the transformation. So we go from sensible heating in the solid ice, latent heating during the phase transformation, and sensible heating again if you keep adding, increasing the enthalpy of the liquid material. So on this diagram here you have H, and here you have the enthalpy that corresponds to the start of fusion, and here is the enthalpy of the end of fusion. The difference between these two enthalpy is the delta H, delta enthalpy of fusion. So what happens during fusion? In fact, the fraction of melt, phi, progressively increases from 0, 100% solid, to 1, 100% liquid. So 0 will be the solid, 1 will be the liquid. How to calculate this? You can, for example, do a linear fit here of this transition between 100, this is phi, this is H. So we have 0, here we have 1, and there will be a linear transition. Phi is AH plus B. If you calculate the coefficient A and B, you will end up with a linear function. Phi is function of H minus H of fusion. Remember, this will be the first value of H here, divided by delta H, which is basically this length here along the axis H. So you can determine phi that varies. Crystallization would be the reverse process. So this means you transform the water into ice. It's the reverse of fusion. but now we go from a high energy material to a low energy material, and there will be a latent heat, which is simply the negative of the latent heat of fusion. So latent heat of solidification will be the negative of the latent heat of fusion. So you just go the opposite way into this diagram. During the solidification, phi progressively decrease from 1 to 0. Melting of pure substances can be measured in the lab, and you can determine the properties such as the delta H of melting. That's an example I took. You can click on this link here. It's actually very nice. It's for the melting of naphthalene. So they do tests in the laboratory, and they measure the heat flow. So they increase the temperature of the sample and measure the heat flow, and you see that you get a peak, negative peak at this moment here. And then when they measure this, they can determine the melting enthalpy and the melting temperature of this material, naphthalene. Of course, it has nothing to do with earth material, but it's a good illustration of how to measure and how to calibrate melting models for pure substances. Now, what's happening is that in the earth, the materials are rarely pure substances. So in geodynamics, the materials usually consist of rocks, which themselves have different mineral phases in different proportions. So, and the different phases which are in the rocks, they all want to melt at a different temperature. So let's take an example. You have a peridotite, which is composed of olivine and pyroxenes. You see the two different mineral phases. And if one wants to melt peridotite, you, I guess, all know that there is a solidus and a liquidus. So the solidus is basically the temperature at which the first melt will be produced. So the most fusible content will start melting. At the liquidus, it means that if you reach liquidus, everything has been molten. So all the components, all the contents of these rocks will be fully molten. So phi will be 0 below the solidus. Phi will be 1 above the liquidus and will vary between the solidus and liquidus. So similarly to the pure substance melting, we can define phi, the melt fraction, which will be the H minus H of fusion over delta H of fusion. This still will apply. The big difference now is that the temperature during melting of a mixture varies during melting. So it has to vary between the solidus temperature and the liquidus temperature. So it's not being held constant anymore. And this we can also determine for the simple case here, that the temperature should vary smoothly or linearly from T solidus to T liquidus as a function of the fraction phi. So here you see the two diagrams which you're going to construct during the exercise. Of course, there are more complexities that should be taken into account. Typically, the solid density or the heat capacity of the solid are a function of temperature, pressure, and composition. But also, the density of the mixture is a phase average, volume average of the density of liquid and the density of solid components. Same for the heat capacity, by the way. In that case, the calculation of enthalpy and temperature becomes a nonlinear function. So you need to have a more advanced treatment of these cases. Additional effects that are important in the Earth system is, for example, when you have multiple reactions. So if you have a system that has several several melting reactions progressively, the melt fraction may not evolve in a linear way between the solidus and the liquidus. Also, we have the effect of water and the effect of CO2, which both impact the position, for example, of the solidus. So you can move the solidus here, for example, as a function of the content of CO2. Compositional effects are also very important. For example, if you have solid solutions, you may have special phase diagrams to see this is a TX diagrams that shows the effect of having a variable content of anortite. Anyways, just before finishing the lecture, let's go back to the calculation of entropy. Remember, the entropy is the degree of disorder in the system, and we have the rate of entropy for the universe, which is the sum of the one of the system and the surroundings. Now, we take the case of crystallization. So in the system, we have water that goes to ice. In the surroundings, we have to receive some heat in a way. So the ds dt system is the Q dot of fusion, latent heat, the rate of latent heating divided by the system temperature. And this would be the rate of latent heating with the plus sign divided by the temperature of the surroundings. So if water turns to ice, the system entropy drops. However, it releases heat to the surroundings, causing the entropy to rise. So we have the plus sign in the surrounding and the negative in the system. So let's make the sum of the two. ds dt universe is now Q dot fusion divided by T surroundings minus Q dot fusion divided by T system. You can factor Q dot fusion, and you get T system minus T surroundings divided by the products of the two temperature. So we have now an equation which is very similar to the heat transfer we discussed last time. You can get ds dt universe to be equal to 0 if everything is 100% ideal or reversible, if the melting is occurring at the case where T system is equal to T surroundings. So it's possible to have zero production of entropy, but it doesn't seem like the most likely case. The realistic scenario is that crystallization will occur if the temperature of the surrounding is cooler than T system. Of course, if you're cooling the material, you will start. It will be easier to crystallize in the system, and if you have the T surrounding which is smaller than T system, then this difference is positive. This product is positive. This is positive, and the SDT of universe is positive. The unlikely scenario is, of course, the case where T surrounding is larger than T system. You don't expect T system to crystallize if it's receiving heat from the surroundings. This is unfeasible, and it would lead to a difference T system minus T surrounding, which is negative, and negative entropy production. So that's basically the end of this lecture. As a conclusion, what we discussed today is melting and crystallization. We've introduced the notion of enthalpy as a measure of energy, and we've discussed the concept of latent heat of transformation. We've introduced a model of melting for pure substances, remember, with the buffered temperature and the linearly increasing phi. We discussed the case of mixtures, where both the temperature and phi increase linearly. And we've also checked the case for entropy production during crystallization. Thanks a lot for your attention.